Continue the lesson, chapter 11, areas of parallelograms and triangles in maths. The next topic we are going to study is parallelograms on the same base and between the same parallels. Here we have an theorem to study. Look into this main figure, children, in which there is ABCD is a parallelogram and EFCD is another parallelogram. Both the parallelograms are on the same base DC and between the same parallels AF and DC. What we have to prove? We have to prove that areas of parallelogram ABCD is equal to area of another parallelogram, that is EFCD. Therefore, the theorem statement is parallelograms on the same base and between the same parallels are equal in area. This is the main figure. This is the given part. What we have to prove? We have to prove that area of parallelogram ABCD. We will represent area as AR. So, area of parallelogram ABCD is equal to area of parallelogram EFCD. Now, in order to prove this theorem statement, let us consider the two triangles in the main figure. Those are triangle ADE and triangle BCF. These are the two triangles, that is triangle ADE and triangle BCF. So, in triangle ADE and triangle BCF, look into the parallelogram ABCD. We know that in a parallelogram, opposite sides are parallel. Therefore, from this figure, you can observe that AD is parallel to BC and AF is the transversal. Here you can observe that AD is parallel to BC and AF is the transversal. We got F shape. When it is F shape, it represents the corresponding angles. We know that if a transversal intersects two parallel lines, then each pair of corresponding angles are equal. Then we get the corresponding angles at angle A and angle B. Mark this in two triangles. It is angle A and angle B. And hence we can write it as angle DAE is equal to angle CBF. It is equal to angle CBF. Consider this as equation 1. Now, consider another parallelogram EFCD. In this also, we get ED parallel to FC and AF is the transversal. Again, F shape is obtained. That is corresponding angles because ED is parallel to FC and AF is the transversal. So the corresponding angles are formed at angle E and angle F. Represent in those two triangles angle E and angle F. And that can be written as angle AED is equal to angle BFC. Consider this as equation 2. Now, look into these triangles. When these two angles are equal, then the remaining angle, that is at angle D and angle C, will also be equal. The reason is, when you add all the three angles, the sum of all the three angles of a triangle will be equal to 180 degree. This is the angle sum property of a triangle, and hence angle D will be equal to angle C, and therefore it can be written as angle ADE is equal to angle BCF. Consider this as equation 3. Now, look into the main figure ABCD parallelogram. We know that in a parallelogram, opposite sides are equal. Therefore, in a parallelogram ABCD, AD is equal to BC. And in the step proof, it is written as AD is equal to BC. Consider that as equation 4 and mark AD is equal to BC in two triangles. Now, look into these two triangles, triangle ADE and triangle BCF. You can observe that the two triangles are congruent if two angles and the included side of one triangle are equal to two angles and the included side of the other triangle. Therefore, we can say that by ASA congruency, we can say that triangle ADE is congruent to triangle BCF. Therefore, in the next step, we can write it as triangle ADE is congruent to triangle BCF by ASA rule, and also by using the equations 1, 3 and 4. In the next step, we will write area, that is used by representation AR, represents area. Area of triangle ADE is equal to area of triangle BCF. In the next step, to prove this theorem statement, let us consider the area of parallelogram ABCD. Consider a parallelogram ABCD. That the parallelogram is formed by the combination of a triangle and another parallelogram is formed, that is triangle ADE and parallelogram EBCD, or it is EDCB. So in the next step, we can write it as area of parallelogram ABCD is equal to area of triangle ADE plus area of parallelogram EDCB. In the next step, we know that area of triangle ADE is equal to area of triangle BCF, and it can be written as area of triangle ADE is equal to area of triangle BCF plus area of parallelogram EDCB. In the next step, area of triangle BCF plus area of parallelogram EDCB will give you the complete area of parallelogram EFCD, and it can be written as together it gives the area of parallelogram EFCD. Therefore, we wanted to prove the statement parallelograms on the same base and between the same parallels are equal in area. Therefore, we wanted to prove area of parallelogram ABCD is equal to area of parallelogram EFCD. And finally, we got in the last step, that is area of parallelogram ABCD is equal to area of parallelogram EFCD, because area of triangle BCF plus area of parallelogram EDCB complete, you get the area of parallelogram EFCD. Hence the proof of this statement. Thank you.